Hello. Thank you for having me. My talk is called Faster Rust Code, Lessons from 7 Years of Speeding Up the Rust Compiler. So I'll start with a little bit of information about me. So I'm a member of FutureWave's Rust team. I have quite a bit of experience with profilers. I've written or co-written a number of the profilers that come with Valgrind, and I've also worked on profilers that are part of Firefox. And I have a decent amount of Rust experience. I'm a compiler team contributor and a member of the compiler performance and binary size working groups. And I've also worked on Rust cperf, which is a performance monitoring framework that we use for the compiler that I will talk a little bit about later on in this talk. So my Rust work is mostly focused on the speed of the compiler, trying to make the compiler faster so that compile times are shorter. This is a topic of interest to many people. It already got a couple of mentions in this morning's sessions, and it's always a topic of ongoing interest. I have a long-running blog series that started 7 years ago called How to Speed Up the Rust Compiler, and I'm now up to about 15 or 16 posts in that. And in these posts, I generally just describe changes that I've made to the Rust compiler to speed it up, and then also some changes that other people work on, and generally just tracking the speed of the Rust compiler. And I've also written something called the Rust Performance Book, which gives a lot of information about how you can make your Rust code faster. And so I'm now going to tell you a little bit about the contents that are in that book and give you an idea of some of the ways that you can speed up your Rust code. So the book basically contains everything that I know about how to speed up Rust code. I wrote the first version of it in 2020, and the way I did it was I basically just went over almost 200 pull requests that I had written, and I just looked at them all and I put them into groups and saw which patterns showed up multiple times, and this basically gave me almost like a chapter layout for the book, these categories, and then it sort of went from there. The book is intended to be a very practical and real-world based thing, so there are links to a lot of those pull requests in the book. So it'll talk about a principle, and then you can see links to actual real pull requests that apply that principle, which I think is important. The book is aimed at intermediate and advanced Rust users. I feel like beginner Rust users have enough to worry about just understanding the language. They probably shouldn't be focusing too much on performance. And the book, even though it's called a book, it's not actually that long. If you print it out, it's probably about 30 pages. Deliberately made it quite concise so that it doesn't take too long to read, so you don't have to spend a long time on it. So here's a screenshot showing the front page of the book. It's available online. It's easy to find. There are about 20 chapters, and that's what it looks like. And so the first topic that the book covers is that of benchmarking. And the idea basically with benchmarking is to compare the speed of two programs that do the same thing. And so you might do this with something like, say, compare the speed of Firefox and the speed of Safari doing some web browser task. And that's where you have two very different programs doing the same thing. But for what I'm talking about, it's more interesting to compare two very slightly different versions of the same program. So you might have revision 1, 2, 3, 4 of your program, and then revision 1, 2, 3, 5, and then you want to compare them, and that can answer the question, how did revision 1, 2, 3, 5 affect performance? And there are a number of aspects to consider when you're thinking about benchmarking. There are things like, what workloads are you using? So what inputs do you have? How are you going to measure it? What tools are you going to use to measure it? Which metrics are you going to measure? And then how do you aggregate multiple measurements together? The benchmarking can be a challenging topic. It can be hard to do well, and it's often quite intimidating, and people feel like they don't want to start. So I would emphasize that, in my opinion, mediocre benchmarking is better than no benchmarking. It's better to have something that does an okay job than if you don't do any benchmarking at all and you're not tracking performance at all, then obviously you can't make any progress. And when it comes to speeding up Rust code, there's a number of things that you can do without even changing the code itself at all, and that involves changing the build configuration. the single most important thing is to do release builds instead of debug builds. By default, the Rust compiler does debug builds. These are a lot slower. If you instead run cargo build -- release, you'll get optimized code. It's quite often people who are new to Rust, they try something and then they post online, I wrote some code and it's not running as fast as I thought. I thought Rust was supposed to be fast. And then somebody says, are you doing a release build? And then they try that and they say, oh my goodness, it's 10 times faster. That's fantastic, thank you. Another useful thing, there's a compiler feature called link time optimization. Comes in two flavors, one called thin, one called fat. The idea here is that at link time, at the very end of compilation, when all your different crates are being linked together into a final executable, the compiler can do some extra optimizations that consider the whole program. And the thin version is a little less sophisticated, doesn't do quite as good a job, but it runs a little faster. And then on a similar note, there's a feature called code gen units that you can adjust. So the idea with code gen units is that the compiler will break your code into a number of chunks and then do code generation on them in parallel. And the reason for this is that it makes compilation quite a bit faster, but there are some optimizations that can be missed because of this breaking it up into chunks. And so if you set code gen units to 1, it won't break it up into chunks. It'll consider all the code in one big single chunk, which lets you do more optimization at the cost of compile time being a little higher. Another more advanced technique is called profile guided optimization. The idea here is when you turn it on, the compiler will, when it compiles your program, it will insert some special instrumentation code into the compile code, and then you can run your program on some representative data, and it will make measurements, and then you can recompile your code, and the compiler will take those measurements into account and optimize the code further. And this can be quite effective. Wins of 10 or 20% are not unusual. It can be a bit fiddly to set up, but there's a new cargo command called cargo PGO that makes it quite a bit easier, so that's nice. And the general theme you'll see here is that if you're willing to pay for longer compile times, you can often get higher code quality. So there is that trade-off there. Now, if we want to actually change our Rust code to make it faster, we need to understand which parts we should change. So the idea here is you need to use profiling to find the hot code that is worth optimizing. Now, there are many profilers available. Each one has its strengths and weaknesses. You may have ones that you particularly like using. That's good. You can see here is a list of profilers that are known to have been used on Rust code successfully. Some things like perf, some of the Valgrind profilers, and so on. And one very important thing to know about if you are going to use a profiler is in your cargo.toml file, you should set debug equals 1, and that will enable debug info. And without that, you won't get file names or line numbers in a lot of the profiling output. So that's a very important thing to turn on. Now, moving on to the actual changes that you can make to your code. A good first example is inlining. Rust has 3 different annotations you can put on a file to say whether it should or should not be inlined. And so the idea with inlining is if you have a hot function, particularly a small one that is called a lot, then the cost of entering and exiting that function will be significant. And if you inline the code into the call sites, then you won't have to pay those entry and exit costs. And it can also facilitate some extra optimizations as well. And so you can often get wins of 1, 2, 3% with inlining. It's pretty easy, but then the question becomes, so how do I know which functions I should inline? And so I like to use a profiler called cachegrind. There's an example here showing what cachegrind's output looks like. On the left-hand side, you can see some counts, and these are the numbers of instructions that were executed at runtime for each of these lines of code. And if you look at the function at the bottom, which is called not inlined, you can see that the first line and the last line have numbers next to them, 400,000 and 200,000. And that shows that how many instructions were executed entering and exiting that function. And you can see the number is quite high. It's similar to the numbers inside the function. And then we have an equivalent function above it, which is inlined. It doesn't have those counts on the first line and the last line, so you can see, that function has been inlined. Another important thing to know about is hashing. So the standard library has hash map and hash set, very commonly used structures. The default hash algorithm they use is very high quality, but it's also very slow. It's called SIP hasher, but there are some alternative versions that use a different hash algorithm. Some of these include FX hash, FNV hash, and A hash. And to give you an example of the effect of this, the Rust compiler itself uses FX hash. I tried last year at one point replacing the use of FX hash with the default hash algorithm, and it made the compiler anywhere from 4% to 84% slower. Now, the compiler does use hashing quite a lot, but still an 84% regression just from using a different hash algorithm tells you how much of a difference there is here. So it's definitely worth using one of these alternatives, or at least trying them to see if they help. And if you find they do help and you choose to use them, it's easy to accidentally reintroduce uses of the default hashing algorithms by mistake, because somebody just doesn't think about it. They just type hash map or hash set. And if you want to make sure that doesn't happen, Clippy, the linting tool, has a lint called disallowed types, where you can specifically ask it not to allow the use of certain types. So you would list hash map and hash set from the standard library, and then Clippy will tell you if you use them by accident. So that's a useful thing to know that a lot of people perhaps don't know about. So the next topic is heap allocations. This is a big topic. Heap allocations are relatively slow. You want to avoid doing lots and lots of allocations and deallocations. So the profiler that I like to use the most for understanding where allocations happen in your program, it's called dhat. It's one of the Valgrind profilers. And then you need to work on these, you need to understand where in Rust code do allocations happen. And so there are some straightforward cases like box and RC and arc that all involve heap allocating a single value on the heap. Then the next sort of obvious case, and a very important one, is vec, which is when you're allocating multiple objects, multiple elements on the heap. And vec always has one allocation and all the elements are in a row next to each other. And if it fills up, it will then reallocate those. And the sequence that it uses when it grows is roughly a doubling strategy. It sort of goes 4, 8, 16, 32, and so on elements. And so it's kind of useful to understand that, the way that works. If you have lots of short vectors, there might be a place in your code that is very hot and it allocates a lot of vectors that maybe have 1 or 2 elements. And there's a good way to avoid those. There's a crate called smallvec, and it has a type in it, also called smallvec. And in that, you can create a vector that has a certain number of elements stored in line in the header structure that avoids the heap allocation. And so, for example, if you have 1 or 2 elements, they would be stored there. And then if it grew beyond that, then it would spill those elements onto the heap. But if most of the cases involve only 1 or 2 elements, then you will avoid allocating in those cases. So that's a technique that we've used quite a lot in the compiler. And then in a similar fashion, if you know in advance the minimum or exact length of a vector and it's reasonably large, you can use functions like with capacity reserve or reserve exact to immediately jump to the right capacity for your vector. And this can be more useful than allocating 4 and then allocating 8 and then 16 and then so on. That can save quite a bit of time. So clone will do heap allocations if the type that you are cloning itself involves heap allocations. So for example, if you clone a vec, because vec is a heap allocated type, the result will obviously be heap allocated. The format macro also involves heap allocations because it's producing strings, and strings are a heap allocated type. When it comes to avoiding heap allocations, there is a standard library type called cow, which is short for copy on write. This can be quite useful. It's very good. One situation it's good is if you have a mixture of owned and borrowed data. For example, you might have strings and then static string slices, and you want to have sometimes use one and sometimes use the other. You can use cow, and it acts a little bit like a wrapper around both types. So that can be useful. Cow is also good if you have immutable data that sometimes needs to be modified. So sometimes you can make a copy of it to modify, but then a lot of the times you won't make it. So cow, it takes a little bit of practice to get used to using cow and understanding it sometimes, but it can be quite effective once you get that understanding. And then by default, Rust uses the system allocator, but the system allocator is generally not as fast as some alternative allocators. So two well-known ones are jemalloc and mimalloc. So in the compiler itself, we use jemalloc, and that is quite a bit faster, and I think that makes the compiler something like 10% faster just by using jemalloc. And it's fairly straightforward in Rust to switch the allocator. There's just a couple of lines you put at the top of your program, and then it's done. And then, so this slide, just to finish the heap allocations section, this is called the Rust Container Cheat Sheet by Rafe Levine. It's a very good summary of how various common types are laid out in memory. So types like box and vec, references, reference counter types, mutex, and so on. It's a lot to take in, and I'm not going to go through it in a lot of detail, but yes, this is a good slide. If you want to take a photo of any one slide in this talk, I would recommend this one. It's really good, or you can look it up online. I understand this stuff pretty well, but I still occasionally refer back to this just because seeing in the diagrams, drawn so nicely is very, very clear for the mind. When it comes to the amount of memory your program uses, sometimes you want to reduce that because it's using too much. And so understanding the sizes of the various types in your program is important. Now, the nightly build of the compiler has a flag called -z print type sizes, which is extremely useful for this purpose. If you run with that, the compiler will print out information about every one of the types used by your program. It'll tell you how big it is and all the information about the layout of the fields and alignment of the fields and so on. And it gives you a lot of information, and you get a really good picture of how exactly that is laid out. And then you might find some surprises. You might find some types that are perhaps bigger than you expected. And then the question becomes, well, how can I shrink those? So one case that's quite common is sometimes you might have an enum, and one of the variants is a lot bigger than all the other variants. So this example I have on the slide, we've got a result type which has two variants, one for the OK case and one for the error case. And perhaps in the OK case, you might have a small type like U32, which is only 4 bytes, but then you might have a very large error type for the error case. And that might be, say, 100 bytes. And in that case, the overall result type will then itself be 100 bytes or more. And in this case, that error case is probably fairly rare. And so a good way to fix this is you can then just wrap that error type in a box, which means that in the result itself, you only store a pointer, and then the error itself is on the heap, and then the resulting type will then only be quite small. Another good way to shrink some types is sometimes if you have integers, you can shrink them. So in Rust, usize is the natural type to use for indexing into arrays and things like that, vectors. But sometimes usize, which is 8 bytes on a 64-bit platform, is more than you need. You don't need that many. So it's possible that a U32 or even a U16 might be sufficient for your particular case. Another technique, there's a type called a boxed slice. So this is an alternative to vector. It's similar to vector, but it's immutable. It can't be grown or shrunk. And so if you have a case where you don't need to grow or shrink a vec, then you can use a box slice, and it's one word shorter than a vector, which might save you some space. And then finally, when it comes, if you have types where the size matters and you've taken the time to shrink them down and save your saved memory, you want to make sure that somebody doesn't accidentally make a change that then makes them bigger. And so you can use the static assertions crate, which has a macro called assert EQ size, and you can use that to check that a type has exactly the size that you expect it to have. And if that ever changes, then you will get a compile error and know that something has gone wrong. So when it comes to standard library types, there's some obscure methods that can occasionally make a big difference, and so there's some things that are worth knowing. So if you want to remove an item from a vector, the obvious way to do it is with the remove method. But the way that works is, imagine you remove an element from the middle of a vector, then you pull that out, and then all the elements above that need to be shuffled down, and that takes time. So if the order of the elements doesn't matter, instead you can use a method called swap remove, and it will remove an item from the middle and then take the last item and move just that and replace that. And so that will change deletion removal from an order n operation to an order 1 operation, which can be helpful. Another good example is some of the common types like vec and string and hashmap and hashset have a method called retain. If you need to remove multiple elements at once from these types, using retain can be a lot faster than if you have to try and remove them one at a time. And then finally, RC and arc have a method called make mute. This one's a little tricky to understand, but once you do understand it, it can be very useful. So the idea here is if you need to modify the value, you can use make mute to get a mutable reference through which you can modify the value. And if the ref count for this type is just 1, it will let you modify it directly. If the ref count is more than 1, then it will clone the value, and then you can modify that. So that occasionally can produce quite drastic improvements. Next is input and output. So the two things to know about here are locking and buffering. So when it comes to locking, for example, the print line macro, which is very commonly used, it locks standard output on every call. So every call to print line, you lock standard output, you do the writing, and then you unlock it. So if you have a lot of print line calls in quick succession, you'll be doing a lot of locking and unlocking. So instead you can just call the lock method to lock it, then you do all your print calls, and then you can unlock it. And that can help. And then for buffering, so file I/O is unbuffered by default in Rust, but it's very easy to make it buffered. So for example, in the case of writing, you can just wrap the relevant type in a buff writer, and this is a big win, because if you have unbuffered I/O, every time you are writing to, say, a file or a network socket, you're having to do a system call. That's relatively slow. And with buffered output, it gathers up a lot of these writes into one and then occasionally does the system call. And so that is good for cases where you are doing a lot of frequent small read and write operations. A couple of things about logging and debugging. So for logging, you shouldn't compute an expensive value and then decide, do I need to log it? Oh, perhaps not. This might seem kind of obvious, but it's surprisingly common. There have been a few cases in the Rust compiler itself where just change it so don't compute this expensive thing if you're not going to print it out. Then for assertions, there's two kinds of assertions, and it's worth being aware of the differences. So the assert macro always runs. Then there's an alternative called debug assert, and that only runs in debug builds. So if you have an assertion on a hot path and it's not critical to the safety of your code, then debug assert might be a good choice. So binary size is another topic of interest. There are a few different things you can do to make your binaries smaller. One is you can choose to strip them, and that removes all the debug info and symbols from the binary. I've seen cases for small programs where this made them 10 times smaller than they would have been with the debug info and the symbols. Another thing you can do is set the optimization level to Z, which tells the compiler, please optimize for compile size. Another thing is you can set panic to abort, and this means that if your program panics, instead of unwinding the stack and printing out a backtrace, it will just immediately abort. And so this way you don't have to include all the unwind machinery, which can make things a lot larger. And this won't be appropriate for every program, but it's appropriate in some cases. So that's 3 different things that you can do. There are quite a few more. There's a repository on GitHub that's called min-sized Rust. It has a lot of good information about reducing the size of binaries. So please check that out if it's a topic of interest to you. If you want to reduce compile times, there's a couple of key things you can do. One is to use a different linker to the default. So it sounds like a familiar story. It's like the allocators. By default, we use the system linker, which is okay, but is relatively slow. There's an alternative one called LLD that is generally a lot faster. If you just add this one line to your cargo.toml file, then you will get much faster linking, and life will be better. Then a more sort of tricky but potentially rewarding thing is if you compile your code with the dash timings flag, you will get a graph that looks like this. And this gives you a great deal of information about exactly how your program is being compiled. So in this picture, every line is a different crate and thus a different invocation of the compiler. And you can see some of them and time is on the x-axis, so you can see some of these take a long time, some of them take a short time. You can also see dependencies between them, like which ones do you have to compile before you can then compile the ones that depend on them. You can see there are places where we are able to compile quite a lot of things in parallel, and then there are parts towards the end where we have, we can only compile one at a time. And so if you see a graph like this, you can sort of maybe look at some of these crates and think, oh, if I've got one crate that's being compiled just by itself and it's very large, maybe I can break that into 2 and then get a little bit more parallelism in there, that sort of thing. Okay, so that's a lot of stuff from the book. There are a few more chapters in the performance book. These cover things like bounds checks and how to eliminate them, wrapper types that can make things more efficient, machine code and parallelism. Please look those up. The book then ends with a number of general tips that aren't necessarily Rust specific, but are still just good to know about when it comes to writing high performance code. And I'll go through some of these now. So the first of these is something that Josh mentioned this morning, which is Rust in general is fast. And particularly if you come from dynamic languages like Python and Ruby, you might find it shockingly fast and not even need to do any of these sort of more advanced techniques to be happy. And likewise, Rust also uses not very much memory. So if you come from language backgrounds like Java and C#, these tend to be quite a lot faster than, say, Python and Ruby, but because they use a garbage collector, they still use a fair amount of memory. And often, if you measure the memory, you'll see this sort of sawtooth pattern where you go up, and then you have a garbage collection, and then you go back down, and then you go up, and then back down. In comparison, Rust tends to use very little memory, and the memory graphs, if you draw them, tend to be much more flat. You don't have these up and down peaks. So that's a good thing about Rust in general. Another point to make is optimized code is often complex. It's more complex than unoptimized code. So you should only optimize code that is hot. That's another topic that Josh mentioned this morning. In general, the biggest wins do tend to come from algorithmic changes and data structure changes, not sort of small, low-level optimizations. But having said that, small optimizations do add up. And so it is really worth looking for both the big wins and the small wins, because they come together well. I mentioned profilers before. I recommend using multiple profilers. If you only use one, you tend to get a certain a certain view on the code. One profiler might be good for finding certain kinds of slownesses, but might overlook some others. So it's good to use multiple. If a profiler tells you that a function is hot, there's a couple of different ways you can improve things. One is to make that function itself faster, and the second way is to call that function less often. Sometimes you can do one, sometimes you can do both. Another thing is that fixing silly slowdowns is often easier than making clever speedups. I used to feel like maybe, because it's surprisingly how often you might find something and the code is doing something that's kind of stupid and that's making it slower. And I used to feel like if you found one of these things and fixed that, that was somehow less valuable or less valid than making some clever speed up. But now I'm just like, hey, if you get a 5% win, it doesn't matter how you get it. It's just they're all as good as each other. So lazy computation can help. So if you do something only when you need to, rather than doing it up front, that's often a good source of wins. Another good general principle is to check for simple special cases before doing complex general cases. Sometimes those special cases are a lot faster and they might be fairly common. Likewise, if you have repetitive data, sometimes you can do data compression to shrink the amount of data. And here I'm not necessarily talking about general purpose data compression like you would get with an algorithm like GZip. Sometimes you can have your own simple, very simple little custom data compressions where maybe a couple of values are handled specially. Another sort of obvious thing but worth saying is that if you have multiple cases, you're checking for multiple different possibilities. You put the most common one first. That will make things faster. And then finally, when you do write optimized code, explanatory comments are really useful. So to just give you an example, you might say 99% of the time this vector has 0 or 1 elements, so handle those cases first. Just a little comment like that can be really useful to other people reading the code to understand why it might be doing something that looks slightly, not the way you would naturally write the code. All right, so that's enough about sort of these ideas on how to make Rust code faster. Now I'm going to talk about, this is how I go about profiling and optimizing code. And so it's a fairly simple process. So something that I just tend to do, I do this over and over again. So I use a profiler to find hot code, and then I just stare at the code until an idea comes. And this is the hard part, but hopefully the things I talked about earlier in the talk will give you an idea of the kinds of things that you can do. And then I make a change and I measure it and I record the result. And if it's an improvement, then hopefully I make a commit, and otherwise I discard it. And so with this process, the staring at the code until an idea comes part, as I said, is the hard part. Often just with time, you just sit there and think about it. Maybe you come back the next day. There have been a lot of times when I've thought, I can't possibly optimize this code anymore. And then a few hours pass and I'm like, well, maybe I could try this. And so that's definitely don't want to give up too early. And so in order to do this process requires a couple of things. So one is you want to have a profiling and measuring setup that's pretty easy and fast to run. So if you can, say, do a cycle that takes 30 seconds to evaluate a change and find out, how has this helped performance, 30 seconds would be good. If it takes 30 minutes to do that, then that's not so good. It's obviously going to take a lot longer to do iterations. You can't do as many iterations. It'll take you longer to do experiments and so on. And as I said before, persistence is key. It's not unusual for me to maybe try 15 different ideas for one particular part of code. And if I do 15, I might get 3 speedups, and then 5 things I try cause slowdowns, and then 7 of them have no noticeable performance effect. And so to follow that up is you want to have some reasonably careful record keeping. If I'm trying 15 different things, I need to write those down carefully. Because with that many things, if you don't write them down carefully, if you try to keep a track of it in your head, you're going to start getting confused about what thing did I try? Did this thing speed it up? Did that thing slow it down? It doesn't need to be terribly fancy, but just have, some way of recording this. So the end result of this process is hopefully something like this. You have a list of successes and some commits implementing those successful ideas. You have a list of failures. If you're lucky, you have a pull request that will be accepted. And a final thing to mention is that it's a good idea to keep these lists around. So I used to, generate these kinds of lists and then just delete them when I thought I'd finished with the code. It's like, oh, I'm done with that. But now I don't do that because often I'll come back to that code 3 months later, 6 months later, and try to remember, oh, did I try that optimization here? I can't remember if I tried that. And then if I have those old notes, I can look at them and find out, oh yes, I did try that and it didn't help, or something like that. So that's a good tip. All right, so the next section of my talk is going to be about tracking performance, because it's one thing to speed up your code, but if you just do it once or you do it occasionally, there's always a chance that you might also introduce slowdowns, and that wouldn't be good. So I'm going to talk about this in the context of the Rust compiler, how we go about tracking performance for the Rust compiler and making sure that it's always improving, because that is the primary goal, to have steadily improving performance. And the way we achieve this, a very important thing is that we measure every single change that gets merged into the compiler. We measure the compiler's performance after that. And the reason we do this is that it's quite often that somebody will make a change that they don't think would have any effect on performance, and then it does. It makes the compiler a little bit slower. And so you need to measure every change. And if you do measure every change, then it's hopefully fairly easy to detect all performance improvements and regressions, assuming that the way you're measuring speed is actually reliable. So we have something called Rust-cperf, which is the way that we do this. So it has two components. The first component is a benchmark suite, which is a collection of interesting Rust crates. And then we have a harness, which is the code that we use to run the compiler on the benchmarks and measure it. So the benchmarks, we have two main categories. In the first category of the primary benchmarks, we have 19 benchmarks. So these are all real-world crates, things that a lot of them you would have heard of, things like Surday, ripgrep, clap, diesel. These are real versions of the crates just pulled from crates.io with no changes, so we're measuring very real-world cases here. And then we have secondary benchmarks, which are a little different. They're things like micro benchmarks and stress tests, sort of extreme examples of code that might stress the compiler, some particular part of the compiler in a certain way. Now, our policy is to review these every 3 years, especially the primary benchmarks. Sometimes we will add or remove a benchmark outside that 3-year review period if we feel that, we will remove a benchmark if we feel it's not being useful anymore, or if we'll add one if we feel like that would improve things. So the good thing about changing benchmarks is that you keep your benchmark suite fresh and representative of the code that people are writing today. The downside is that changing benchmarks does interrupt your data. And so we also have a third category of benchmarks that we call stable. We have 10 here. And the idea here is to provide the long view of like 5 years or more. And so what this means is that these benchmarks haven't changed in a long time, so they're quite old code. They're not necessarily representative of the code that people would write today in Rust, but they do give us that very long data sort of series. So there's a number of different configurations that we measure the compiler in to sort of reflect different ways that people use it. There are 4 different profilers: check, debug, opt, and doc. And then we have a number of different scenarios for different ways of invoking the compiler using incremental compilation and non-incremental compilation. And you put profilers and scenarios together, we end up with at least 13 compiler runs for each benchmark. So that's quite a lot. We're testing it in quite a lot of different ways. And if that means a full run of the of the whole suite, the 40-something benchmarks that we have over 500 different compiler runs. So it's quite thorough. Then there's the question of metrics. What are we measuring? And we have 5 main ones. So the number of instructions that are executed, the wall time, the number of cycles, the peak memory, and the size of the compiled artifacts. So of these, you might think that wall time was the most important, because wall time, that is what matches a user's perception of how long compile takes. They're thinking about it in terms of this is taking a certain number of seconds. They're not thinking about it in terms of this is taking a lot of cycles. And so wall time would be the ideal metric, except that it tends to have a reasonably high variance. It's not unusual to have 1, 2, 3% variation from run to run, which means that it makes wall time, it's hard to detect small improvements or small regressions when you've got that kind of variance. So instructions executed is probably the metric that we look at the most, because it has much less variance. It's not an ideal metric in a number of other ways, but it is very reliable. And when you're comparing 2 very similar versions of the same program, the number of instructions executed is actually a pretty decent metric. So that's why we use that. In terms of how the measurements are done, we measure them with perf, the standard Linux profiling tool. The results go in a database. You can view that through a website. And so here's an example screenshot from the website. Here we've got 8 different graphs. The top 4 are for one benchmark called cargo-060. The bottom 4 are for a crate called clap 3.1.6. Each of these graphs covers a period of about 6 weeks. And you can see over time that most of the lines are fairly flat. There's a couple of small drops which indicate places where we made small improvements to the amount of compile time. And so that gives you a nice sort of time-based overview. We also have another view where it's a more text-based view where you can compare 2 points in time and find out all the changes. In green, changes in the change column indicate things that got better, and red indicates things that got worse. And so that's another good way of looking at the data. And then this one shows results from those stable benchmarks that I mentioned earlier. This is a much longer time period. Here, this graph goes from the current day all the way back to Rust 1.28, which is about 5 years ago. So this gives you a sort of a rough idea of how the compile times have dropped over that 5-year period. This is for debug builds, but if you look at the other kinds of builds, the graphs look fairly similar. So from this, it's clear that the compiler genuinely has got faster over time, which is very important and very good. So rustcperf, as I mentioned, it's run after every merge, and the results from that run get posted into the GitHub pull request automatically by a bot. There is a heuristic that evaluates, did this improve performance or did it regress performance? This heuristic is aware of some differences on a benchmark basis, so some benchmarks are naturally noisier than others, and so you need to be aware of that. The heuristic is also, it's not completely perfect. Sometimes it will make a wrong evaluation, and so we have a kind of a backup step where every week there's a person who goes through and checks through all the results and makes sure that nothing important has been missed. So here's an example of a comment of that sort. So you can see at the top of this it says overall result, improvements, so no action is needed. And then we have a table for the instruction counts, and you can see that the first 2 rows in the table are about regressions, and there were no regressions, so that's good. And then the next 2 rows show improvements, and you can see we had 184 improvements to the primary and 153 to the secondary, and so this was a very good pull request that made a good performance improvement. If it was a regression, then the label at the top would say, the results are bad, action is needed, please reconsider whether it needs to improve things somehow or back this out. And then finally, so rustcperf supports profiling as well as benchmarking. You can run the compiler under many different profilers. These include the compiler's own self-profile, profiling infrastructure, perf, cachegrind, dhat, a few others, a variety of different profilers. One important case is cachegrind, which supports diffs, so you can profile one version of the compiler, compiling a crate, and then another version, slightly different version, compiling the same crate, and then you can compare the two different cachegrind profiles, and then it will tell you exactly what changed in terms of the compiler as for why it got faster or slower, and that can be very useful. And adding new profilers is fairly easy, and something that we do anytime a new profiler comes out. So Sampley, the last one on the list, is a fairly new profiler, and so we added support for that, and that's been quite useful. I've used that quite a bit. All right, so that comes pretty much to the end of my talk. So a few items to sort of summarize. So I think that profiling and optimization, it does require persistence. It's not super easy, but it is doable with a bit of effort and a bit of thought. Similarly, tracking performance does take effort. Unfortunately, it would be nice if you could do it in a fully automated way. In my experience, you can't do that. You need some level of human intervention to just to check that your automated processes are working well. But that's also something that's worth putting effort into if performance is important to you. Then in general, I think Rust is a really great language for writing high-performance code. I think Josh had that exact phrase in his talk this morning. It's just a really nice language. And finally, if you want to read the performance book, please check out this URL, because that's where you will find it. All right, and that's the end of my talk. Thank you.